Hey YouTuber, my name is Gyanendra Kumar Sa and I'm working as a power electronics engineer in ATI Motors Private Limited in Bangalore, India. This is my first educational video where I will be taking you through various steps used in designing inductors in detail for both AC and DC application and some common mistakes performed while designing inductors. So there was these two questions which I was really troubled when I was designing my first inductor in undergraduate. So the first question is which formula to choose for calculating the number of turns required for making inductor. So there is one formula which is given by AL value and the one formula which we have derived from the Ampere's law. So which one to choose? You may be thinking that the both formulas will give the same design and the same requirements, but you believe me, they don't give the same results, and we have to choose the one among both for given requirements, and one suits better for one design requirement, and another suits better for other requirements. Okay, and that will be completely understanding throughout the video. And the second question was like whether we need air gap into the core or not. So you may have seen some inductors where you don't have air gap, and some inductors you have air gaps. In some case you have very huge air gaps in the range of centimeters and all. So what basically decides the air gap? So that also we'll be looking through in the video. This is the flow of video. So first actually we'll be going through few basics only related to designing inductor, and then we will be talking in detail how to design inductor for DC and AC application, and then we will be listing the steps which we can follow for designing inductor from scratch, and then we'll be going through the two design applications where we'll be using ferrite and iron powder toroidal cores to design, where we will be completely seeing the difference between using these two formulas. Okay, so let's go ahead. So in inductor basically we'll be having one winding, and hence there will not be any other mutual windings over there, so it will be mostly dominated by self inductance. So what is the definition of self inductance? So the definition of self inductance in a brief can be explained by this. So let's say we have a I flux characteristic, flux versus I characteristic. So the characteristic of flux versus current can be drawn something similar to this, where I am ignoring the hysteresis nature of the phi I characteristic. So we'll see that from point A to 0 and to A dash, you'll see that more or less the curve is linear. So more or less curve is nothing but linear. Okay, now in this linear region, basically the inductance is defined by the slope of phi I characteristic. So since the inductance, this characteristic is linear in this region, as a result our inductor will be constant from region A to A dash. So this is where inductance is constant. If you start going beyond these points, let's say you are going away from this A dash, then what will happen? The slope, if you see, the slope is starts decreasing. Okay, and when the core is completely saturated, you will see that there will not be any slope. So that means inductance will be zero. It will act as a short. So it will lose completely its property of opposing the change in current into the inductor. Hence, it's very important when we design inductor, so to operate in the linear region so that our core will not go in saturations, and our inductor will not lose its property. So now onward we will be focusing on this linear region where we'll be assuming that the phi I characteristic is linear, and hence the inductance is constant over the period. And the general expression for the inductance in this linear region we can write by phi by I, where phi represents flux, I represents the current. So you take any coordinate in the linear region, the slope you can find like phi minus 0 by I minus 0, because it's passing through origin, so it's nothing but phi by I. So that is for one number of turns. If you have n number of turns in the coil, then it will be multiplied by n. So this equation one represents the basic definition for the self inductance. So let us consider this basic magnetic circuit where we will be using this for analyzing our inductor design steps. So let us consider this core where the cross-sectional area is uniform throughout the core. It has winding of number of turns as n, and let's say this is the path where the flux is built, and this is the length of the magnetic path. So this line denoted by dotted here is nothing but the magnetic length path, that is core length path also you can say, and the cross sectional area of the core is AC. So these are the few nomenclature being used for designing, for analyzing the design of inductor. So phi represents here the magnetic flux into the core, AC represents the cross-sectional area of the core, Lm represents the magnetic path length, N represents the number of turns in the coil, I represents the current flowing into the coil, B represents magnetic flux density, H represents magnetic flux intensity, R represents the magnetic reluctance, where this is very important parameter while designing inductor. This plays a very important role, which we will be going in detail. Then mu represents the relative, mu represents the permeability of the medium, where mu naught is absolute permeability, mu r is the relative permeability of the medium. So to understand that this magnetic circuit which we have taken, so the fundamental law which we can use for analyzing that magnetic circuit is Ampere's law. So what is Ampere's law? According to Ampere's law, if we integrate the magnetic flux density over a closed path, any closed path, then it will be equal to the product of permeability of the medium and the current enclosed by that closed path. So in this magnetic circuit, if you see, let us consider this the closed path denoted by this dotted line. Okay, so in this case, if you see, the total current enclosed is nothing but N into I, because there are n number of turns, and hence we can replace that I enclosed by nothing but n into I. And if we assume the magnetic flux distribution is uniform throughout the magnetic path, then we can say that magnetic flux density is constant, and hence we can take that B out of the integral symbol, where it will be just left with the integral of path length, which is nothing but magnetic length. Okay, so now this is the reduced relation for uniform magnetic distribution. So this is for uniform distribution of magnetic flux, and if we simplify that further, we'll get this expression where the B is replaced by flux per unit cross sectional area. So this expression further we can replace Lm by mu AC by symbol R. So basically what is being done, the Lm by mu AC is replaced by R, which is called as a magnetic reluctance, which is analogous to electric resistance, but they are not completely analogous. Like the electric resistance actually dissipate energy, but magnetic reluctance, they store energy. Basically the magnetic energies are stored in the reluctance, but not dissipated. Okay, so this expression contains basically a different form of MMF. MMF is nothing but magnetomotive force, which is responsible for building magnetic flux into the magnetic circuit. So these are the different way of writing MMF, which if we just take this phi r was actually introduced by Hopkinson's, and hence that is called as a Hopkinson's law. Okay, now if we combine the basic definition of inductance and the Hopkinson's law, we will see that the relationship between inductor and the reluctance of the core can be obtained. Let's say if the number of turns in a core is constant, then you can see the reluctance and inductance are inversely proportional. So higher the reluctance, less the inductance, and less the reluctance will be having higher inductance. So this is one more very important relation while designing inductor, which we will be using frequently. So basically there are two equations which we will be using more frequently in designing inductor. One is this equation 3, one is this equation 2. So everywhere we will be using these two equations to design the inductor. So what is basically need of air gap into the inductor? If you see the reluctance formula, you will see that mu is in denominator. So basically reluctance and mu are inversely proportional. So if it is a magnetic material, there will be some relative relative permeability, that is mu r. So for magnetic cores like ferrite, we have very high number of relative permeability. So for example, the grade like CEL HP3C grade ferrite core will have relative permeability of 2000. Hence, the reluctance of core is very very low. As a result, what happens? To understand the effective the side effect of having low reluctance, let us solve this those two equations which we discussed just now. If we solve these two equations where we eliminate the number of turns, we'll get this relation. So what it tells is, if you want some inductance, you have some inductance requirement. So for that, your Im will be fixed, your value of inductance will be fixed. If you have already selected the core, your AC will be also fixed. So in that case, you can see the relationship between B and R. So least the reluctance, what will happen for lower value of current, you will see that the flux will go very very high. So hence, for designing magnetic circuit, that is in this case inductor, we have to choose the proper value of reluctance. So the reluctance of the magnet inductor should be high enough, so that for the maximum current, the flux into the core will be less. Okay. Yeah. So this is basically the whole idea about having the like, if this you have least inductance, then this is the problem you will be facing. Okay. So now what happens if we introduce the air gap? So to answer that, let us draw the phi I characteristic once. So without air gap, that is a pure magnetic material, you will see that the phi I characteristic will be something similar to this. So if you see carefully, in the linear region, the slope is higher. So the slope is higher in the magnetic material when there is no air gap. As a result, in you have inductance higher. But if you see, with very low current, as it is a more step, low current is with very low current flowing into the inductor can make inductor to go in saturation region. So that's a problem without without having air gap. So what happens if you introduce air gap? So after introducing air gap, what happens? The slope of the phi I characteristic reduces, and it goes like this. So basically, the slope of phi I characteristic is reduced. That means inductance has reduced. If inductance has reduced, we already know that L is equal to N square by R. That means reluctance has increased. So this is with air gap. So the black one is representing with air gap what it will be. But if you see what is the advantage here, the current which was saturating the core without air gap, now that current is will not you will not saturate the core if there is a air gap. So basically the current required to saturate the air gap inductor will be higher than the without air gap. Okay. So this is basically what happens if we introduce air gap. So after introducing air gap, what happens? Like our current handling capability of the inductor increases. But parallelly, what is happening? Our inductance is also inductance is also decreasing. Okay, so there is a upside of it also, but there is a downside of having air gap also. One more very important thing is, while introducing air gap, is if we introduce the air gap, what happens? The fluxes has to pass all the way through this air gap. As a result, what happens if the length of air gap is high or the more, then the fluxes will start moving away from the main geometry of the core. So they will start bulging out. That is called as a fringing of flux. So because of fringing of flux will increase as the length of air gap increases. Okay, so now it may happen that if the length of air gap goes higher, then some fluxes may leak out. Some fluxes may go away from the main magnetic path, and that may create noise for other power signals, or some they may create EMI EMC issues, like so. The proper cares and all, like proper shielding and all, is very important. But anyway, if we introduce the more air gap, what happens is they start leaking out. Okay, so that again affects our inductance value and our magnetic property. Okay, so this air gap is a problem if you increase to a very large number. So these days, to tackle with that problem, what is being done? So let's say this is the same core. So instead of providing a big air gap into one place, let's say this is the air gap was required. This is the length of air gap LZ. So now, instead of providing a big air gap into one place, what is being done? We have provided the distributed air gaps. Instead of provided the lumped air gap, the whole air gap are being distributed throughout the core. So how it's being done is some non-magnetic materials. So the core, inside core only, the non-magnetic materials are used to fill the materials throughout the materials, so that we get the suitable reluctance required for meeting the inductance specification. Okay, so in this case, what will happen is the flux leakage will reduce by very large number, and we will be able to still get the suitable inductance and current rating of the inductor. Yeah, so this is the this is called as actually air gap distributed air gap core. Okay, yeah. So now okay, so let us assume these are few variables, like LG is the length of air gap, length of core. Length of core is nothing but from this point, if you go throughout the core and come back here, this length is nothing but the core length now. So basically, it's basically the length of the magnetic circuit minus the air gap length. So that is core length, and these are the reluctance for the corresponding core and air gap. And mu r is a relative permeability of the core, and mu naught is our absolute permeability of the medium. So this is basically medium. Okay, so for air it is, it's basically absolute permeability, which is not of medium. It is like, it's with respect to vacuum, or you can say air. Okay, yeah. So the total reluctance is nothing but the addition of reluctance of core and the air gap. So we know that the relation of reluctance is nothing but Lm by mu AC. Mu can be expanded as a mu naught into mu r, and for core there is a mu r, but for air you can say that the mu r is almost 1. So, and we know that mu r is a high number for magnetic materials like ferrite core and all. So because of that, this the core reluctance is very very less compared to the air gap reluctance. and hence we can approximately say that if we introduce air gap into the core, the total reluctance of the core is almost same as the air gap length. So in that case, as we know that the reluctance is the place where the magnetic energy gets stored, so all the energies in that case will be stored into the air gap. Okay, yeah. So this is what happens if we introduce the air gap, and yeah. So let's go to our actual topic where we want to design the inductor. So what are the steps we need to follow? So the first thing one has to know is what they want. So basically, what value of inductance they want, what current rating, frequency of operations, what type of core they want, so that they can place in their PCB. They may be having toroidal pod core requirements. So basically, those requirements needs to be clear before proceeding with the design, and they should also know whether they are using in DC or AC application. So these all things needs to be clear beforehand. Okay, so now after that, the main important thing comes is selection of core. So there are different types of core available. You can pause the video, you can see the cores here, you can search them in a Google also. The image is not that clear. Okay, now yeah, so there are many types of core, and you can choose any core which you feel good for your design purpose. How do we select the core? So there is a two methods which is generally adopted for selecting the cores. So the first method is core selector chart, and the second method is area product method. So let us take the first one, that is core selection using core selector chart. So what happens now, we know the inductance value, its current requirement. So we can find Li square, that is nothing but proportional to our the magnetic energy. So basically, what amount of energy you want to handle, you want the core to handle. So in using that, you can just find what energy you the core needs to handle. Then you can spot that number into the x-axis. Then you can go up, find the intersection on this black line. So wherever it gets intersect, you can choose the core. You can choose the core, all the cores above that line, above that point basically. So you can choose, let's say the intersection is here, you can choose this core, or the cores above there, or you can choose the cores here and above there. So basically this is a very simple method, but the problem here is, like, you have to get this correct the chart. And for this I have got from the magnetics, so they have provided this chart for for designing, for selecting the cores, but some other manufacturers may not provide this. So depending upon the manufacturer data sheet, or the availability of the data, you can choose the methods. Okay, so this is first method, which is very simple for using. Okay, so the second method is area product approach. So what is area product? So basically we will be having some space for placing windings. So where we will be placing windings. So the where we place the winding is nothing but called as a window area, where we can insert the conductors and wind the windings. And the cross sectional area of the core is nothing but called as a AC. Okay, so the product of this window area and the cross sectional area of the core is called as a area product. Okay, so now we need to find this expression. We need to find the formula for area product. So let us take our basic Hopkinson's expression, where we have BAR is equal to Ni. So this AC is nothing but the cross sectional area of core. So this cross sectional area of core we can find like nothing but Ni by Br. Here we want to design the inductor for maximum current Im and maximum flux density Bm. Hence the I and B are replaced by Im and Bm. Okay, so now how do we find the window area? So to answer that, let us take this. Let us say this is a window. Basically, this part is core. This is core, and this part is nothing but our window area where we can place the windings. Okay. Now let us say we have to place the conductors inside this. So let's say we are placing conductors here which has some cross sectional area. So I'm drawing big conductors here, but the conductor sizes may change according to the requirement. So let's say the area of each conductor is AW. Okay. Now you will see one very interesting fact that there are areas which are not utilized even after placing the windings very close to each other. So what is the whole thing is we cannot utilize the 100% of window area for placing the windings. There is only few percent of window area we can utilize for placing the windings. Okay, so that factor, that is nothing but called as a kW. So kW is nothing but the window factor which is defined as the percentage of window area which you can utilize for placing the conductor. Okay, so generally for inductor, for single winding inductor, you can choose for initial designing to be on the safe side that the windings will for sure will fit into the window area. You can choose as a zero point 0.6. So basically, zero point 0.6 you can choose for initial design, but actually people have gone till more than zero point 0.9, like around 0.95 also people have achieved. But those are professionals. So if you are a beginner, you better choose a zero point 0.6 and design. If you are a you are professionals and all, and still you are a student, you want to design for the project, you can still go with zero point 0.8. So zero point 0.8 also you can safely choose, but I'll recommend to choose zero point 0.6 if you are if you started just designing inductor. So what is the idea then? So what we can say is the kW times window area is nothing but will be the area occupied by the n number of conductors. So let's say AW is the cross sectional area of the each winding or the each conductor. How do we find the cross sectional area? So that cross sectional area of the each wire we can find like how depending on the current capability of the wire. So we are designed for some RMS current or the maximum current. Okay, so depending on that we can find what is the cross sectional area. So this is IRMS divided by the current density. J is nothing but current density, and we can replace IRMS by IM by KC, where KC represents our this thing, the crest factor, which is defined by IM by IRMS. Okay, so this after substituting the value of AW here, we'll get the simplified expression for the window area. Now we know the window area expression, we know the cross sectional area expression. If we multiply them, we'll get this as a result. Okay, which is nothing but area product now. And if we can further simplify by replacing n square by r by L. Okay, so this is actually our the final expression for area product, where L we know all the parameters before we will be knowing all the parameters beforehand to select the course. We know inductance, current rating, then kW you can choose according to your need. Kc we will be knowing, like for DC you can choose as a 1. If you want to do some calculations, you can still find the ratio of maximum by RMS, but choosing one will definitely not alter our calculation by much difference, because DCs are RMS and IMAX are a bit closer. J you can choose as a 3 ampere per mm square. For AC design, it's better to choose 3 ampere per mm square, or else you can choose 5 ampere per mm square also. So these are the two common numbers. For DC you can go with 5 ampere per mm square for sure. Okay, now how do we decide BM? So how do we choose BM? So basically we decide the BM depending upon the power the power losses into the core. So this is for ferrite core, like P-type material at 180 degrees Celsius is being taken from the magnetics. So they have given some notes from where I have taken it. and you can see so different frequencies, for different frequencies there is a different graph. Okay, so now it tells that you can see as the frequency is increasing, the core loss into the magnetic circuit is also increasing. It's obvious that as the frequency increases, the waste of energy, also the frequency of waste energy, hysteresis, and eddy current also increases. Okay, so now one interesting fact you will see that as the frequency is increasing, our the maximum flux density which we can use in a circuit is also reducing. Okay, so now how do we choose the maximum flux density? So depending upon your core material, your manufacturer will provide the data sheet something similar like this. So the good number to go with is 100 milliwatt per centimeter cube, where this is the loss which will be happening in the core, and then you just point out where it belongs. Okay, so you can just see for your frequency operation. So let's say we want to design it for 25 kilohertz. Okay, so for 25 kilohertz, if you see it's actually not intersecting, so you can see that you can go still higher flux density. Let us say we are just choosing the 2000 Gauss. So basically what happens is we have to find the intersection for 100 milliwatt per centimeter cube, and then choose the corresponding for frequency plot. You see where it is intersecting and choose that as a your flux density, that is as a BM. So let's say for 250 kilohertz it is intersecting around 600 Gauss. So this you can choose as a BM, but it's not like you have to choose 100 milliwatt per centimeter cube only. You can go higher also, you can go lower also according to your thermal management of your PCB or your power converters. Yeah, so this is the one methods to find BM, which is very effective. And it's given in Gauss, so you can find in Tesla by using this expression. So 10 to the power 4 Gauss is nothing but 1 Tesla. Okay, so now what we do is we got the area product formula. We calculate the uh, you know the value of area product for our inductance requirement, and we choose a core which has a area product higher than the one we computed, and we choose the area product from the catalog of the the core provided by the manufacturer. So you can look on the different size of core which meets the area product requirement. So this is very important part where I'll be explaining. I'll be answering the first question. Actually, the first two questions will be answered here itself. So there is two formula which using which we can find the number of turns. So the one is using Hopkinson's law or the reduced form of Ampere's law. You can we can like this is the these are the two expressions. The main expression which we have already derived in the beginning itself. So if you solve these two equations, you can find the value of number of turns here. So basically, R is being eliminated, in the both the cases, R and yeah. So now this is the one equation using which we can find number of turn, and there is one more variable which is provided by all manufacturers. So you can find the value of AL of the core in almost all the manufacturer data sheet, and this is the very commonly used by many manufacturers or small scale industries, big scale industries also. Okay, so now this is the another formula. If you see, the AL value is defined as the inductance you get per unit square of number of turns you have on the core. So basically this is defined as the AL, and if you see it carefully, this L by N square is nothing but reciprocal of reciprocal of reluctance, which we can see from here. Hence, we can say that AL is nothing but permeance of the magnetic circuit, that is reciprocal of reluctance. So the basic thing is you choose this formula or this formula. So whatever formula you choose for finding number of turns, the basic idea is the flux density of the magnetic circuit should never exceed the maximum flux density for which you are trying to design. So ultimate thing is B should be less than Bm. If you see the first expression, this N formula, it is always being taken care here, because here the maximum, here the current term is also there, which by using which we calculate number of turns, so that our BM requirement is being fulfilled here. So this formula is already taking care of that thing. But this, if you see, there is just inductance and number of turns. There nowhere we are talking about Bmax, and nowhere we are talking about the Im. So how do we cross verify? So if we use this AL formula, we have to cross verify that we are not going to enter into the saturation region. How do we do that? So let's say we get the value of n from this formula. So n will be nothing but square root L by AL. Okay. So what we do is we find the number of turns from here, and this B we can get the relation from here. B is nothing but Ni by AC R. Now this I we can replace by Im, and Ni by RAC. Okay, so this is same thing, B we have got. So basically that B has to be less than or equal to Bm, and 1 by R we already know that is nothing but AL. Okay, so that AL value we can compute from this expression, but we don't know the now we know we don't know exactly number of turns. Let's say we don't know number of turns there. We have not substituted the value of n from there here. Now let us replace this n. Before knowing the number of turns only, we want to cross verify whether AL value is, we can go ahead with that formula or not, because while designing we cannot check all the formulas and then we say that will be time consuming. So we have to come up with some strategy. So to come up with strategy, let us replace this n now. So this value of n is being replaced using this formula, that is nothing but root under L by AL. So after substituting these all formulas and simplifying them, we'll get this as a inequality. So you will see that if we use this formula, then this inequality has to be met. If it is not satisfied, then we can say that whatever value of n you have calculated from here, for sure, for the Im, for the maximum current, if it flows into the core, your B will reach the Bm. It will not just reach, it will exceed. It may exceed to a very large number also, if the proper care is not being taken care. So basically, what is this is the main deciding factor between choosing the formulas among those. So if this is being satisfied, this is satisfied, then we can choose this AL formula. Okay, if this is wrong, then we have to go ahead with this formula. So this is basically deciding factor. If you see carefully here, this is nothing but 1 by R, that is permeance. And if this is not this is not satisfied, that means this one is greater, this one is greater than the requirement. So basically this is nothing but the permeance which is needed for the getting the suitable inductance requirement. But if this is greater than the permeance, what will happen? Your reluctance is low. So the reluctance of circuit is low. As a result, what will happen is your reluctance is low. Hence, even so, reluctance is lower than the reluctance required. As a result, what will happen? For the Im current flow, the B in the circuit will exceed the Bm. As a result, the inductor may go into the saturation region. And if this is satisfied, you will see that this is lower than the permeance. That means the reluctance of the core is already greater than the reluctance required. So in this case, there is no problem. The reluctance of core should not be lesser than the reluctance required here, but it can be greater than, so that will not create a problem. Hence, if we analyze that way, we can also conclude that if this inequality is followed, then we need not to introduce the air gap, because the reluctance of the core is sufficient enough without air gap. But if this is not being followed, then we have to introduce the air gap. So basically the answer of both questions was raised is nothing but is done by this inequality. So in conclusion, what we can say is, we first for calculating number of turns, we first check this inequality. If this is being satisfied, then we use the AL formula for calculating number of turns, and there is no need of introducing air gap. If you have this inequality is wrong, then we have to choose the Ampere's law formula, and we need to introduce the air gap, the formula which we'll be discussing later. So this is the basically the methods to calculate the number of turns into the for required inductance. Now the wire gauge selection. So wire gauge selection, this is the place where we talk about AC and difference between AC and DC inductor. So for DC inductor, we know that the cross-sectional area of the wire is fully utilized. So basically the whole area of wire is utilized for flowing the current. So current flows all the way. Hence we can simply calculate the cross-sectional area of wire required as nothing but using this formula, Im max by Kc into J. Okay, so this will give us the cross-sectional area. Again, you can choose Kc as one. For the AC inductor, it's not as simple as this one. If the cross-sectional area of the wire is not correctly selected, then the problem like this may occur. Let's say this is a cross-sectional view of the wire where the red is actually showing the intensity of current flowing into the wire. So we can see that the current flow into the wire is not uniformly distributed in AC case. The majority of currents are pushed near to the corner of the surface of the wire. So basically, so the majority of currents are flowing near the surface of wire. They are not flowing into the core of the wire. There is just few negligible amount of currents are being flowing. So there is what this is basically the skin effect of AC current, because of which we have the higher effective resistance than DC resistance, and we have to then we have one more term here, that is skin depth. So skin depth is nothing but the depth from the surface of conductor to which the majority of currents are flowing. So you can see this the depth denoted here is nothing but called as a skin depth. So the general expression for skin depth is given by this, but for frequencies less than 1 by rho epsilon, what we can say is we can assume this term as a 1, and hence we can say that the skin depth general skin depth formula to reduce form will be this one. So this rho is nothing but resistivity of the conductor. Your omega is the angular frequency, and mu is nothing but your permeability of the medium. So permeability of the wire. So basic for copper wire, the permeability of relative permeability of the copper wire is nothing but 1, and hence the permeability is nothing but absolute permeability in case of copper. And resistivity of copper wire, this number I have taken from the Google. So after substituting these numbers into this equation, we will get the reduced form of skin depth as this formula. So you can see higher the frequency, the skin depth goes on reducing. As a result, what happens if we increase the number frequency, the cross sectional area of the wire also keeps on decreasing. So as the cross sectional area of wire is decreasing, the problem comes here is like getting the required higher current rating. Okay. Now we know that as the cross sectional area is reducing, the current carrying capability of wire also reduces, and hence we have to connect many wires in parallel to get the suitable current rating. Okay. So basically, how do we decide what cross sectional area we have to choose? So we already know the skin depth. If we choose the twice of skin depth as the diameter of the wire, then we will be almost utilizing the full cross sectional area of the wire, where the currents will be flowing throughout the wire, and hence we can say the almost 100% of wire will be utilized for current flow. And the cross sectional area we can find like a pi skin depth square, where skin depth is nothing but radius of the conductor. So we need to get the suitable current rating also. let's say because of this skin effect, we got a wire which can handle only 1 ampere current, but our current requirement is 50 ampere. So we have to connect 50 number of such wires in parallel to increase the current rating to a 50 ampere. So we can do that by using this formula, where Im by kcj is nothing but the total cross sectional area required. If we divide by the cross sectional area of this wire, then we can get the number of wires to be connected in parallel, that is nothing but np. Okay, so this is how we can find the cross sectional area and the suitable current rating of the wire we can choose. This is the wire selection table, where standard wire gauge is being used here. So we have here the bare conductor area, then diameter with enamel, the coating diameter and also is important. Then weight per kilogram, all those things are being mentioned, which we'll be using while we design the inductor. Okay, now, so we should cross check our calculations also, like our design. It's not like we designed all the number of turns and then the parallel bunch we have to make, all those cross sectional this core geometry, all this thing we decided, but the basic thing is the all windings should fit into the core. If they don't fit, then definitely we have to redesign, we have to select the core with a higher dimension. Okay, so how do we check? It's a same basic formula, where we have this kW into window area has to be greater than or equal to your the total cross sectional area of the is the wire which we are going to use. So for DC also, what can be done is we can connect many wires in parallel. Let's say our current requirement is 100 ampere. So you can choose wire for DC application. You can choose current of wire of current rating 100 ampere also, not a problem. But what problem will come while winding them into the core? Okay, so if you choose a 100 ampere wire, then you cannot wind it very without mechanical, like without machine and all. It's very difficult to wind them. So what we do is we can take the wires of current rating like 5 ampere or 10 ampere, and we can connect them in parallel, and hence the winding them over the core becomes much easier compared to the winding 100 ampere wire. So this formula we can again use for DC and AC. So if there is just one wire you have used, not the parallel bunch of wires, so you can make NP as 1. This will work for both the cases. So as we discussed earlier, if air gap is needed to be introduced, then this is the basic formula which we can use for finding the length of air gap. Okay, so let us summarize the steps which we have discussed. So first step is, of course, we have to know the inductor specifications with these numbers, these details, and then we have to select the core. So here onward, I'll be taking area product formula for calculating, finding the number, finding the core, so that graph for finding core is easier. One can follow it very easily. So we'll take up the area product formula. Then number of turn calculation. So basically we follow this algorithm. So we just check inequality. If it is justified, we need not introduce air gap, and we use AL formula for calculating number of turns. Otherwise, air gap needs to be introduced, and then we'll use the Ampere's law formula for calculating number of turns. Wire selection, for DC you can use this one, where for low current you can use this one. In AC you can use the finding skin depth, where this is a general formula, how many number of parallel wires you have to connect, and this formula you can use for DC also if the current requirement is very very high. So this is the wire selection criteria. Then we have to cross check. So for DC I have made it separate, for AC I have made it separate, but this in general can be used for both the case. You just make NP as a 1, if one wire is used. Then air gap, if required, we can calculate. So these are the summarized steps which we can follow for designing inductor. So let us take this example and design inductor. So let's say in our power converter where we are operating at, we want to operate at 25 kilohertz in DC application. Let's say DC converters like buck or buck boost in any converter, and our inductance value has come to like 500 microhenry, and our maximum current which we want to operate is 5 ampere. So for this application we want to design an inductor. So I have taken two cores here, two toroidal cores. One is using ferrite core, one is using iron powder core. So we'll be taking both and then we'll be giving you the design. So basically the choosing two different core material is to demonstrate the the difference in using the formulas, the number of turns formulas. There are two formulas. So in ferrite core we'll be using, actually you will see that the Ampere's law formula works better, and in iron powder we that AL formula works better for finding number of turns. Let us go step by step. So ferrite core. So we have to find the area product formula where we have this formula. Inductance value we know, IM we know. For ferrite core, the BM value you can choose for 25 kilohertz, zero point 0.2. Just now we saw the graph from where you can see 0.2 is a safe number. You can still go 0.25 for this frequency operation. 25 kilohertz you can go still 0.2, 0.23 or something, 25. Then window factor I have taken as 0.6. Kc is 1. G is nothing but 3 ampere per mm square I have taken, the lower safe number. Then you will get the AP area product if you convert into centimeter to the power 4. You should not forget that this is the product of two areas. So it's a power 4 here. Okay, sometime if you write square and all, it will be very difficult for you to, you will lose the track here itself, and you will get all the wrong answer in the next steps. Okay, so now how do we select the core? So as I told, we need a toroidal core. Okay, so now I have yeah, so this is a catalog I have downloaded from Magnetics website. Okay, so let me zoom in here. Yeah, so this is the for toroidal core, and you can see the different dimensions are being given here. So if you see here, this B is nothing but your inner diameter, A is nothing but your outer diameter, C is your thickness of the core. So depending upon those things, the cross sectional area is also given, and window area is also given. So basically window area we also have, cross sectional area also we have. So you can find the product and you can meet your requirement. So our requirement is like we want the area product of around 3.4722 centimeter power 4. So you can find the product of the cores and you can select your required AP product. Yeah, so these are the two cores which I have highlighted here. So you can see if the area product of both are higher than that, and you can see these cores lower than lower from here are also having area product higher than the required one. So you can choose any one, but it's better to choose the closer one. So if you see, if you multiply this and this, it will be more than 4 or something. It will be more than 4.5 or something. And then if you multiply this one, you'll see that it will be lesser than this and closer to our APU requirement. So this core is being chosen. Okay, now we have to see its AL value. So this core AL value, if you can see, the same part number is here. So there are different materials. So these numbers, these alphabets are telling they are different grade material. So you can choose any core depending upon your requirement. So basically for high frequency SMPS, you can use this RPF cores. So I have chosen this R because the inequalities AL should be low. So I have chosen the least among all. Okay. So that is the, and cross sectional area, all those things I have noted down here. So basically this is the core being selected. You can download its data sheet from Magnetics and you can look back, cross check the values also. So basically it's a P type, it's a which type material, R type material. So basically it is R type material. Okay, fine. So now these are the AL values, and if you see, the AL value is not given in a straight forward manner. It is given in different fashion. So you will see that it is given in millihenry per 1,000 turns. So, and we, what we want is Henry per turn, okay, per turn square. So to do that, milli you can multiply 10 to the power minus 3, and these are 1,000. But we know that in denominator we have number square, so we have to square it, and hence we'll get the converted answer as this. So basically, this we ultimately we want to convert into Henry per turn square. So this you can use for conversion. Okay, then area of core and a window area is given here. Okay, sometime this AW will not be given. So what we can do is we will be knowing this inner diameter. So inner diameter we can use for finding window area also. So there, so you can follow some geometry calculations for getting your numbers if they are directly not given. Okay, so this is your number of turns check. So you check this inequality. So we already know all the values. So BM is 0.2 and a cross sectional area we got. IM we know, inductance value we know. So if you see, after putting these numbers, we'll see that this AL value has to be less than this. But if you see, this is actually much greater than the one we want. So this is completely false. That means we cannot use this AL formula. We cannot use it. We'll see what happens if we use that. Hence, we have to use this Ampere's law formula, and you'll see that number of turns is coming like 53.64. You can go ahead with the next integer number, that is 54. Let us say, let us see if we use this AL formula, then what will happen? Just to cross check, let's see. Now, if we use this formula, we have this inductance and AL value. You will see that there is a very big difference. There is a big difference between number of turns computed from here. This is giving 54, and you can see this is 8. They are very far away from each other. So now you will see so if you do winding of 8 turns without providing any air gap, you will be for sure getting the inductance of 500 microhenry. Okay, so you will get inductance, not a problem. But what will happen if you pass the current of 5 ampere? You will see that, so this is to cross check, if I pass 5 ampere current, what is the flux density it is going to give? So inductance value, this is the same calculation. So a number of turns I have used as 8, which we got from this AL formula. You'll see that the flux density, you can see the difference. The flux density for 5 ampere, it is coming 1.3837, which is way away from zero point 0.2. So you can clearly say that if 5 ampere flows through it, what will happen? The core is completely going to saturate. You will not be able to even go to 5 ampere. Till what current? At what current you will see B will become Bm. So you just do again the same thing where you just replace B by Bm, find I. You will see that you wanted to design for 5 ampere, but you see at 0.7227 only, and 227 only ampere, you will be reaching 0.2 flux density. So you can see, if you don't do the cross check and if you just do windings and check the inductance, you will see that 500 microhenry is coming. I'm very happy. Now inductor is being done. But if you put in a real circuit, real power circuit where current starts flowing, you will see the problem. You will think that the circuit should operate correctly, but they don't. So it's very important to not just getting the inductance value. It is also very important to get its current rating also. So here this AL value has completely failed. We cannot rely on this. You can see it will be really good if we have 8 number of turns and we can meet the current and flux density requirement, but they are not. So we have to provide 50 54 number of turns. Okay, 54 number of turns with suitable air gap to to get the correct reluctance of the material. Okay, so this way just to give you idea that what can happen if you don't take care of the proper design. Then wire selection, we already know what is the maximum current we want. This one I have made as 1. So yeah, if you divide this, you will get in mm square. So 1.667 mm square of wire you need. So from the table which I showed earlier in wire selection, you can choose the cross section. You can choose a wire which has a cross sectional area greater than this and closer to that. So the closure value was SWG16, for which cross sectional area is given as this. Okay. So now we have to cross verify whether all the windings can fit into the core or not. So for finding cross check, for finding the cross sectional area of the wire, we should, if you see here, this area whatever I have listed is the bare is the bare conductor cross sectional area. But the cross section area which you need to take care in window area check is with the enamel also, with the insulation also, because that will also be there. Okay, so you should take the diameter or the cross sectional area with enamel. You find that area used for cross verifying. So 0.6 is like 60% of window. Let's say we are going to utilize window area was we got from data sheet. Then this area we just now computed 54 number of turns, and we see that thus this inequality, if you compare this, all things are in mm square. So this is in mm square, this is also in one second. Yeah, so these all units are being made in the same dimension, and hence you can, yeah. So basically this area product is being followed, and you can say that these things are gonna to work. Okay, so the windings can be placed into the core. You can cross verify those numbers and you will find that they will definitely match. Okay, now, so as we had checked that the inequality is not matching, so length of air gap we have to compute using this. So we have to provide the air gap length of 1.7075 mm. Okay, approximately 1.7 mm air gap you have to provide. Now the problem here is it's a toroidal core, so you have to provide the air gap of this much length, but you have to cut it. So you have to use advanced machine like water jet cutting or laser cutting to get this precision of. Okay, if you start cutting by your hexo blade or some other blades, you know what will happen, you'll end up with some error. So in toroidal core, generally it's better to choose toroidal core only when the air gap is not needed. Okay, so what people do is if they feel like they are going to have a big like air gap and all, and in toroidal it's difficult. That's why you can choose some other cores like double E core, ETD core, EI core. So any other core which is for which very easy to provide the air gap, just you have to separate and put some insulating materials in between, and that length you can definitely match. So this is basically double E core with air gap is being shown here. Okay, so now it is very important one thing here, why I have chosen double E core to give you a feel of the equivalent reluctance. So here if you see, if you provide a air gap here, okay, so it's not just air gap there, all the places you are providing same, let's say same air gap you have provided everywhere. Okay, so now you will see that there will be all the where air gap, so this will also have some reluctance, this will also have some reluctance, and all the parts will have some reluctance. And if you see this core, there is no air gap between these two, but there is only one air gap in between here. So only central limb is having air gap. So providing half air gap here is same as providing like the double of this air gap here. So basically what happens, let's say if you have this kind of arrangement, and the LG is the length of air gap. Okay, so let's say LG is the length of air gap, and mu naught by AC is nothing but your reluctance. Okay, so in that case, if that is the air gap, okay, let us take this circuit. So let us take this circuit diagram. So we have this E core. So let's say this is your length of air gap. Length of air gap needs to be introduced. The cross-sectional area for this is A. I'm assuming the cross-sectional area of the outer limbs are half, and we will be placing windings here. Okay, so as we are going to place the winding here, this let's say the reluctance of this part is R. So this reluctance will be 2 times R. Why 2 times R? Because the reluctance is given by L by mu A. So L is same in all the cases. If you see cross sectional area is half there, so this will become half, it will become 2R. So this reluctance here is nothing but twice the reluctance here. So if we write the electrical analogous, you will get something like this. This is 2R, 2R, 2R. This is your MMF. So if you find the equivalent reluctance, you will see that it will come to 2R. These two are in parallel, it will become R, and then in series they will become 2R. So that is what is being shown here. So the equivalent reluctance is nothing but twice the reluctance of the central part. So in that case, you and then equivalent reluctance you can write like n square by L. So here the interesting thing is the whatever air gap formula you had we have used here, it's not exactly same. It's like divide by 2 here. So whatever air gap formula which we have shown there is nothing but we will get half of the air gap. So let's say there it was like 1.7 or something. So half of that we will be requiring air gap if everything is same. So what I'm trying to say is, if you are choosing a core, it's better to find equivalent reluctance of the whole magnetic circuit. Use that R equivalent equal to n square by L for finding length of air gap. Okay, otherwise you may just use that formula, get the length of air gap as 1.7, will provide length of air gap here 1.7 all the places. You will see that the inductance will not be the same that you are expecting, and actually you will end up with lesser inductance and the current capability to go more higher, which is not desired. Okay, so that was about ferrite core. So generally ferrite core for high power applications, we don't use toroidal core. If you have distributed air gap which has because of which we can have higher reluctance, then definitely we can use the toroidal ferrite core. Why I'm saying that, because if you see the AL value, they all are pretty high. There is nowhere AL value we have less. So because of this AL value is high, the reluctance of the cores are more. The reluctance of the core are less. Okay, and because of that we need to have some air gap for increasing its reluctance. Now let us come to the iron powder core. So this core is a different material, and it has different chemistry, and because of which the maximum flux density we can go higher than zero point 0.2. So the actually speaking, the maximum flux density one can go till point 6 to 0.8 also one can go, and depending on frequency it's comes down. So for 25 kilohertz 0.35 we can choose as a safe number, but still it's a DC, so in DC we'll have less losses, so you can go till 0.5 also, but let me choose 0.35. Okay, so all the parameters are same, everything is same, just I have made it as a 0.35. You'll see that the area product has value has reduced. It was earlier 3.7 something, now it has become just 1.98, so it has reduced by a lot actually. So because if you choose the proper core with a higher flux density, your actually core size also comes down, because your product area product requirement is getting down. Then we have to select the core. So how do we select the core? This is the official website of Micrometals, where these are the toroidal cores. So if you just click in products and toroidal, you will get this space, and yeah, you can choose the core. So now you will see here there is no direct the window area given, but we know internal diameter. So this internal diameter you can use for finding the window area, and cross sectional area, you know, so you can find product. So I have done those calculations, and this T150 core will help. Okay, so T150 core you can select. So whose dimension is like this is this is given in inch. So okay, those calculations one can do, and we can get. You will see one interesting thing is this what T150. If you see, there are a lot of T150 cores. Okay, and if you see the dimensions is exactly same. All the dimensions are same. So what is the difference? So difference is in AL value. So depending on your material, your you know, if so depending on material, their AL values are different. So this is what is different. So if you are designing something and you need some AL value, you can choose accordingly also. This is an advantage over here or other magnetic cores also. Okay. So now our requirement is that 1 point. Uh, yeah, cross sectional area is 1.98. So we can choose T1 150 core. And how do we choose the AL value then? Okay, so that is again a very interesting thing. So I have chosen T15060. I'll tell why I have chosen this AL value. Okay, so basically what you can do is, in this case, if you just find this number. Okay, so you can find this number. This is what the AL value should be. So maximum AL value can go as this number. Okay, so basically 77 we have got 77 nano henry per ton square. So if you can choose the core with the flux, the AL value which is less than but close to that 77, then what can be done is you can you can the difference between the number of turns which you get from the both formulas will actually starts reducing. Okay, but we cannot get exactly 77 if because manufacturers may not have. So you can choose accordingly. So I have chosen T150 15060. Yeah, it's here, it says 65. There is 66 also, you can choose this also, not a problem. Yeah, so basically this cross check is again a very it's also helping in a one case. If your area this, now you can see it is being justified here. Now the AL condition is being justified here. So what you can do is in using this, then if it is justifying, you can choose the suitable core with suitable AL value also. Okay, after choosing that correct core, now we have seen that this is justifying. So you can find the number of turns from here itself. So you can see it is coming like 88 around. So we can have to have 88 number of turns just to cross check what happens. So B we are computing from the number of turns we have got from there, inductance value, current, and AC, all these things are same. We have got like 0.32 which is definitely less than 0.35. So hence our this B less than BM is constraint is being justified. Just to cross check, let us find the number of turns which we get from the Ampere's law. Now you will see that the number of turns which we need we got from that AL value is actually more than this number of turns which we got from this Ampere's law. So does it mean that we can use 81 number of turns and get the inductance value? No, we cannot get, because this formula is actually using whatever this formula is being using. For that AL value is 77. Okay, but our AL value is 65. So basically the reluctance of our core is bigger than the reluctance for which that Ampere's law formula is being using. So that is why we introduce air gap to increase the reluctance. We don't introduce, there is nothing we can do for reducing the reluctance. So we can introduce air gap to increase reluctance. We cannot do anything to reduce the reluctance, and hence we cannot use this. If we use this, then what will happen? According to your this formula, your the value of inductance will get computed, and you will not be getting the required number of inductance. Okay, so that is what is being told here. Okay, so wire selection is the same method. So you just find the cross sectional area, and yeah, so that's the same procedure. So wire selection will not change, and then cross check. We again got the same calculations, and yeah, then multiplying those numbers and all, and you will get the answers. So here also we can see it is being justified. So do we need air gap? No, not required, because AL value is justified. So uh, what is in conclusion, what we can say is the number of turns, there are two number of turns formula. So one has to check the inequality, that AL inequality, and from there only we can decide which formula to go ahead. And hence there maybe we don't need air gap, we need air gap, so we have to verify those things. So basically the objective of this video was to answer that questions correctly. Hence the two examples were selected, which clearly indicates that the one example tells that we need air gap, one example tells that we don't need air gap, and toroidal core is better. And you can see using iron powder core, actually the cross sectional, the area product has come down. So as a result, size of core has also come down. So there are a lot of good quality the cores also, which you can look in websites like Magnetic Micrometals, your other websites, um, DigiKey, your yeah. So there are a lot of places you can look up and you can design. If you have any doubts, or you want to suggest something, and yeah, so for if I have done some mistakes, you can put those things in comment, and we can correct those things. Yeah, so I'd like to thank you for being with me for this video, and if you really liked, so please hit the like button and subscribe the channel. Thank you.